alkyl iodides are more denser than alkyl bromides, which are more denser than alkyl chlorides, which are more denser than alkyl fluorides. The branching is inversely proportional to boiling point. As branching increases, the boiling point decreases. Para isomers have 70 to 100 degree more than that of ortho and meta with respect to their melting point. Polar compounds are completely soluble in water anta helirtivi. But alkyl halides, although they are polar in nature, they are insoluble in water. Hello, my dear students. I am Renuka Ashok, Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Today is the third session of chapter Haloalkanes and Haloarenes. Third session of chapter Haloalkanes and Haloarenes. Okay. Now, last class, that is in the second session, I discussed about nomenclature of haloalkanes and haloarenes, nomenclature of haloalkanes and haloarenes, nature of CX bond, as well as methods of preparation. Okay. Today class, I am going to explain the physical properties as well as chemical properties of haloalkanes and haloarenes. Physical properties as well as what? Chemical properties. As you know, the physical properties means, under physical property, we will have to study about color, smell, nature, boiling point, melting point, solubility, density, all these comes under which property? Physical properties. Under chemical properties, we have to study about reactions. How the compounds reacts with metals, how they reacts with non-metals, how they reacts with acid, how they reacts with base. This comes under chemical properties. Therefore, today I am going to discuss about the physical properties as well as what? Chemical properties of haloalkanes and haloarenes. Haloalkanes and haloarenes. Let us consider first one, the physical state and smell. Smell also odor. It is also one we can word odor. Haloalkanes are colorless. Haloalkanes are colorless and sweet smelling liquids. The lower members like methyl chloride, methyl bromide, ethyl chloride are colorless gases. Okay. Now, generally they are liquids. Most of haloalkanes are liquids. Most of the haloalkanes are liquids. But lower members means methyl chloride, methyl bromide and ethyl chloride are gases. Okay. Higher members having high molecular mass, they are solids. Therefore, in haloalkanes, most of the members are liquids. Lower members are gases, and higher members, that is having high molecular mass, they are solids. Next, density. Bromo-iodo polychloro derivatives of hydrocarbons are heavier than water. They are heavier than water. Density is known as mass by volume. Density is nothing but mass by volume. Allige, the molecular mass is directly proportional to density. Molecular mass is directly proportional to density. As molecular mass increases, density also increases. Therefore, which is more having density? Iodo, next to bromo, next chloro, as well as what? Fluoro. Alkyl iodides are more denser than alkyl bromides, which are more denser than alkyl chlorides, which are more denser than alkyl fluorides. Next, the very important topic, the boiling points as well as what? Melting point. Boiling point and melting point. Boiling point and melting point are related with molecular mass. Molecular mass is directly proportional to boiling point as well as what? Melting point. Why? Greater the molecular mass, as molecular mass is more, the stronger will be its van der Waals force of attraction. Stronger will be its it's van der Waals force of attraction or interparticular force of attraction or intermolecular force of attraction. Therefore, the molecular mass, as molecular mass increases, the van der Waals force of attraction also increases and boiling point or melting point also become high. For example, I'll take same alkyl group R. Okay, I'll consider Ri, RBr, RCl, RF. Here, what you observe? Alkyl group are same, only I am changing halogen, iodine, bromine, chlorine as well as fluorine, which has high molecular mass iodide. Therefore, the boiling point order is Ri. Alkyl iodides have higher boiling point and melting point than alkyl bromides, than alkyl chlorides, than alkyl fluoride. Therefore, for the same alkyl group or aryl group, boiling point decreases as which has high boiling point, alkyl iodides, which has low boiling point, alkyl fluorides. Therefore, the molecular mass is directly proportional to boiling point or melting point. For the same halogen, the boiling point decreases as the size of the alkyl group decreases. For example, X, same here. Okay, here it is propyl, here it is ethyl, here it is methyl. This group is propyl, this group is propyl, and this is ethyl, and this is methyl. It has how many carbon? 3 carbon, 2 carbon, 1 carbon. So observe here. So halogen atom is same, that is X, but alkyl group are different. In the first compound, the alkyl group is propyl. In the second compound, the alkyl group is ethyl. In the third one, alkyl group is methyl. As the molecular mass for the same halogen atom, the molecular mass increases, the boiling point also increases. Here, the boiling point decreases as the size of the alkyl group also decreases. The very important point, for your competitive NEET as well as JEE. Observe here, these are isomeric alkyl halides. These are isomeric alkyl halide. When I consider this halogen atom as chlorine, okay, it is one chloropropane. It is one chloropropane. This is 1, 2, 3, 4. So now it is 1 chloro, it is 2 chloropropane, and here I will consider 1, 2 ತಗೊಂಡಾಗ it is 2,2-dimethyl. 1 chloro 2,2-dimethyl propane, as well as it is tertiary butyl chloride. It is tertiary butyl chloride. Okay. Observe here, in isomeric alkyl halide, boiling point decreases as the branching increases. Observe, it is linear. It is linear. It is 1-bromobutane. It is 1-bromobutane. It is 2-bromobutane. It is 2-bromobutane. It is okay. Observe here. Here the branching is more compared to this. It is linear. It is branching. In the forward direction, you observe here the branching increases. As branching increases, boiling point decreases. As branching increases, boiling point decreases. Alige branching is inversely proportional. Branching is inversely proportional to boiling point. This is for isomeric alkyl halides. Boiling point decreases as branching increases. In the forward direction, the branching increases. Nodi, when it is less branching, its boiling point is 375. Next, somewhat it branching increases, it becomes 364. Here also once again branching increases, it becomes 346. Therefore, in the forward direction, as branching increases, the boiling point decreases. In the first case, the boiling point is 375, here 364, and here it is 346. Therefore, once again I will repeat. So, there are three cases, A, B, C. For same alkyl or aryl groups, for same alkyl group or aryl group, the boiling point decreases as Ri is more than that of RBr, more than that of RCl, than that of RF. For the same halogen, the boiling point decreases as the size of alkyl group decreases. Observe in the forward direction, here the bigger alkyl group, here smaller, because it has 3 carbon, it has 2 carbon and it has 1 carbon. As the alkyl size decreases, the boiling point also decreases. But here in the third case, the branching is inversely proportional to boiling point. As branching increases, the boiling point decreases. This is because as branching increases, what happens? The molecule acquires spherical shape. Molecule acquires or attains spherical shape with less surface area. Less surface area. This is a very key point for this. Okay. So what happens? As branching increases, molecule acquire or attains spherical shape. As it attains spherical shape, it has less surface area. When surface area decreases, its interparticle force of attraction becomes what? Weaker. As force of attraction is weak, it requires less temperature to boil. Therefore, it possesses lower boiling point. Once again, I will repeat. What happens? As the molecule become more and more branching, it attains spherical shape. It attains spherical shape and it has less surface area. When it has surface area, as a result, the interparticle force of attraction become what? Weaker. Therefore, it has required low boiling point. It require what? Low boiling point. Okay. Now, I'll consider haloarenes. Okay. The boiling point of dihaloarenes are nearly the same. Observe here. Boiling point. These are called as dihaloarenes. Why they are called as dihaloarenes? Because they contain 2 halogen atoms. This is 1,2 dichlorobenzene. This is 1,3 dichlorobenzene. And this is 1,4 dichlorobenzene. When you consider the boiling point of dihaloarenes are nearly same. Nearly the what? Same. Observe the values. Boiling point. First case 453, it is 446, it is 448. There is a small difference between boiling point. But when you consider melting point, the melting point of para isomer generally 70 to 100 degree higher than the melting point of ortho and meta. So, when you consider the melting point, the para, here it is which one? Para. How can you say it is para? This position is ortho, this position is meta and this position is para. Okay. When you consider para isomer, its melting point is 70 to 100 degree centigrade more than that of ortho as well as meta. This is ortho isomer and this is what? Meta isomer. This is known as what? Meta. This position is ortho and this position is known as what? Meta. So, ortho as well as what? Meta. Ortho as well as what? Meta. Para isomer whose melting point is 70 to 100 degree centigrade more than that of ortho and meta. But boiling point of dihaloarenes are nearly the same. Okay. So, why the para isomer has high melting point compared to ortho and meta? Because of plane of symmetry. Its symmetry. Because of its plane of symmetry. Because of its symmetry, para isomer has close packing in its crystal lattice. Close packing in its crystal lattice. In crystal lattice, it has a close packing of its molecules in the crystal lattice. When consequently, when the molecules are closely packed, okay, they require strong intermolecular attractive force. Therefore, usually usually in your competitive, if they ask which one has, out of this compound, which one has high melting point, means student, the option is 100%, it is para. You please tick the answer where the compound name starts from the word para, because para isomers have 70 to 100 degree more than that of ortho and meta with respect to their melting point. This is because para isomer is having plane of symmetry. It has a close packing of molecules in crystal lattice. In a crystal, when it has close packing of molecules in crystal lattice, it has strong intermolecular force of attraction. So this is about regarding about what? Melting point as well as what? Boiling point. Solubility. Already I told that alkyl halides are polar in nature because X is more electronegative than R. Delta minus, it is delta plus. Molecule is polarized. Therefore, alkyl halides are polar in nature. So, although they are polar in nature, alkyl halides are insoluble in water because they are not able to form hydrogen bonds with water. Why alkyl halides are insoluble in water? Although they are polar in nature. Usually, now chemistry lo en helirtivi, polar compounds are completely soluble in water anta helirtivi. But alkyl halides, although they are polar in nature, they are insoluble in water because they fails to form which type of bond with water? Hydrogen bond. As a result, the energy required to overcome the force of attraction between the molecule of haloalkanes and that required to break the hydrogen bonds between water molecule is more than the energy released when new attractions are set up between haloalkane and water molecule. Okay, the force of attraction break the hydrogen bonds as well as haloalkane, overcome more than the energy released when new attractions are set up between haloalkane and water molecule. Here, main point you think, remember, they are polar in nature, they are insoluble in water. Why they are insoluble in water? They fails to form hydrogen bond with water. Next, I finished the physical properties. Move on to chemical properties. The reactions of, I'll discuss first the reactions of haloalkanes. I want to discuss three types of reactions in haloalkanes. First one, nucleophilic substitution. Second one, elimination. Third one, reaction with metal. Elimination reaction is also called as dehydrohalogenation. It is called as what? Dehydrohalogenation. What are the three important chemical reactions I want to discuss under reactions of haloalkanes? Under reactions of haloalkane, three important reactions are nucleophilic substitution, elimination reaction, nucleophilic substitution reaction, elimination reaction, as well as reaction with metal. Let us consider first one, nucleophilic substitution. What is nucleophile? Nucleophiles are rich in electron. Those species are rich in electron. They are called as what? Nucleophile. Nucleophile generally they carrying which charge? Negative charge. In this, substitution means what? One is replaced by another one. Okay, now substitution ಅಂತ ಹೇಳ್ತೀವಿ. ಅದರ ಬದಲು ಇದನ್ನ ಹಾಕೋದು ಅಂತ. ಅವರ ಬದಲು ಇವರು ಅಂತ ಹೇಳ್ತೀವಲ್ಲ, ಅದನ್ನ ನಾವು substitution ಅಂತ ಕರಿತೀವಿ. Here also in this type of reaction, one nucleophile. Okay, here in this type of reaction, the nucleophile having which charge? Negative charge, attacks the partially positive carbon. Partially positive what? Carbon. So, avaga this halide X is get CNU bond is formed and the halogen atom leaves as halide ion. Before, see, observe my student, here delta is what? Minus, it is plus. Okay, when I add nucleophile carrying which charge? Negative charge. Why nucleophile carrying negative charge? Because it is rich in electron. So, this nucleophile attack carbon. Why it attack carbon? Because it is partially positive. As nucleophile attacks carbon, there is a formation of new bond, that is carbon nucleophile bond is formed, as well as X is detached from carbon and it is comes out in the form of halide ion. Therefore, here during nucleophilic substitution, there is a formation of new bond. What's the formation of new bond? The formation formation of new bond is carbon nucleophile. Carbon nucleophile. And which one is get detached? Halogen is get detached from carbon, as well as it leaves in the form of what? Halide ion. X is come out in the form of what? X minus. This reaction is called as what? Nucleophilic substitution reaction. Now, alkyl halides undergo nucleophilic substitution reaction with so many reactants, so many reagents. The first one, aqueous KOH. First one, aqueous KOH. KOH is potassium hydroxide. It is also called as potash. It is also called as potash. What is aqueous KOH? KOH is dissolved in water, is aqueous KOH. Instead of aqueous KOH, one you can take aqueous NaOH. What happens when alkyl halide is heated with aqueous KOH? Here the nucleophile is X, here nucleophile is OH, it is minus, here exchange of nucleophile takes place. X is replaced by OH, therefore RX become ROH, therefore which compound is formed? Alcohol. Which one is formed? Alcohol. Okay. Therefore, what happens when alkyl halide is heated with aqueous potassium hydroxide or aqueous sodium hydroxide? Aqueous potassium hydroxide or aqueous sodium hydroxide. Aqueous potassium hydroxide is also called potash. Here, what is the general formula of alkyl halide? RX, potassium hydroxide KOH. Here in case of alkyl halide, nucleophile is X, in KOH OH, X is replaced by OH. Example, in place of R, I'll take ethyl. Ethyl, X bromine plus KOH, it is aqueous. It is aqueous. In the parenthesis, if you write AQ, it indicates that it is aqueous. The solution is prepared by using water. Here which is nucleophile? Br. Here it is OH. Therefore, replacement adre enagutte idu CH3, CH2, OH plus KBr. This compound is ethyl bromide. Its trivial name, IUPAC name is bromoethane. IUPAC name is bromoethane. Here the compound form is ethyl alcohol. IUPAC name is ethanol. IUPAC name is ethanol. Okay. Similarly, next you take alkyl halide heated with alcoholic potassium cyanide. Alcohol means here the potassium cyanide dissolved in alcohol. KCN. K is potassium, Cn is cyanide. Here X is nucleophile. Here Cn, it will form RCN plus what? KX. In place of R, you put methyl as well as what? Ethyl. Methyl bromide as well as ethyl chloride heated with alcoholic KCN. Here nucleophile is Br, here Cl. It is replaced by Cn. It will become methyl cyanide. Methyl cyanide is trivial name, as well as its IUPAC name is ethane nitrile. IUPAC name is ethane nitrile. See, because of the functional group, if Cn is present, it is known as what? Nitrile. It is known as what? Nitrile. It is known as propane nitrile. Cn is present, it is nitrile. How many carbon atoms are there? 1, here 2. Therefore, it is propane nitrile. Therefore, dear student, what happens when alkyl halide is heated with alcoholic potassium cyanide? There is a formation of alkyl nitrine or cyanoalkane. Alkane nitrile or cyanoalkane. Next, with alcoholic AgCN, silver cyanide. That is silver cyanide. Here, there is a formation of alkyl isocyanide, or it is also called as carbyl amine. So, carbyl amines andre carbyl amines are alkyl isocyanide. Cyanide is Cn. Isocyanide is Nc. Cn is cyanide. Cn is what? Cyanide. Nc is what? Isocyanide. For example, once again you consider methyl bromide and ethyl chloride. Here AgCNL nucleophile yavado? Cn. Br is replaced by Cn. Chlorine is replaced by Cn. But here attack takes place through nitrogen, not it is Cn. Here functional group is what? Nc. Cn is cyanide, Nc is what? Isocyanide. Cn is cyanide, Nc is what? Isocyanide. Dear students, Here, in both the cases, first case I had taken alcoholic KCN, second case I had taken alcoholic AgCN. But in both the cases, nucleophile is Cn minus. Nucleophile is Cn minus. But in the first case, in case of which one? Potassium cyanide, there is a formation of cyanide. There is a formation of cyanide. Here in case of AgCN, there is a formation of what? Isocyanide. Isocyanide. When you use potassium cyanide, you will get what? Cyanide. When you use silver cyanide, you will get what? Isocyanide. When you use potassium cyanide, carbon is the attacking center, nucleophilic center. When you use AgCN, which is attacking center here, nucleophilic center, nitrogen. Therefore, nucleophile is same, cyanide. But once it attacks through carbon, once it attacks through nitrogen. Therefore, Cn minus is called as ambidentate nucleophile. Ambidentate nucleophile. Cn is called as what? Ambidentate nucleophile. Ambidentate nucleophiles. What are ambidentate nucleophiles? The groups such as cyanides means what? Cn minus. Nitrite means what? NO2 minus. They possess two nucleophilic centers. Two nucleophilic center. Artha agtidya? Nucleophile 1, nucleophilic center 2. Molecule is same, but nucleophilic centers are 2. Such nucleophiles are called as ambidentate nucleophiles. Like what are ambidentate nucleophile? Nucleophiles having two nucleophilic centers. Two nucleophilic centers are called as ambidentate nucleophile. Very good example for ambidentate nucleophiles are Cn minus and NO2 minus. Cn minus and NO2 minus. That is, when you are taken KCN, they will form alkyl cyanides because potassium cyanide is ionic in nature. It gives Cn minus ion and Cn minus ion attacks carbon atom of haloalkane through carbon. When you take potassium cyanide, it is being ionic in nature. It split up into K plus and what? Cn minus. This Cn minus ion attacks carbon atom of haloalkane through carbon to form cyanide. To form what? Cyanide. Next I will consider AgCN. AgCN, it will form isocyanide. KCN form cyanides, AgCN form isocyanide. Being covalent in nature, they does not ionize. They does not produce Cn minus ion. Therefore, the lone pair of electrons which are present on nitrogen, which are donated to carbon. Therefore, nitrogen donates carbon lone pair of electron and it will form what? Isocyanide. Therefore, in both the cases, the nucleophile is Cn minus. In case of KCN, it attacks through carbon. In case of AgCN, it attacks through what? Nitrogen. When it attacks through carbon, it will form cyanide. When it attacks through nitrogen, it will form what? Isocyanide. Why? In case of KCN, there is a formation of cyanide. It is in ionic nature. Why in AgCN, attacks takes place through nitrogen? Because it is covalent in nature. With silver salt of carboxylic acids. Silver salt of carboxylic acid. What's the general formula of carboxylic acid? RCOOH. If H of carboxylic acid, if it is replaced by silver, that is Ag, it is called as silver salt of carboxylic acid. What's the general formula of silver salt of carboxylic acid? RCOOAg. Alkyl halide is Rx. Ag takes X and it will form AgX and it will form RCOOR. or COOR. If any compound containing COOR as a functional group, it is called as what? Ester. It is called as what? Ester. Therefore, what happens when alkyl halide is heated with silver salt of carboxylic acid? When alkyl halide is heated with silver salt of carboxylic acid, ester is formed. Ester is formed. Now I'll take silver acetate. Silver acetate. What's the formula of silver acetate? CH3COOAg. And I'll take methyl iodide. Ag plus I, it will give rise to AgI and it will form CH3COOCH3. This is methyl acetate. Methyl acetate. Next to silver ethanoate. C2H5COOAg. Plus I'll take other alkyl halide, ethyl bromide. Ag takes Br and it will form AgBr and the compound is C2H5COO, C2H5. It is ethyl ethanoate. Ethyl ethanoate. Therefore, what happens when alkyl halide is heated with silver salt of carboxylic acid? When alkyl halide is heated with silver salt of carboxylic acid, there is a formation of ester. There is a formation of what? Ester. Next, formation of alkyl nitrites. When they heated, when alkyl halides or haloalkane are heated with alcoholic potassium nitrite. Alcoholic potassium nitrite. Here I'll take alcoholic silver nitrite. Here it is potassium nitrite and here silver nitrite. See my dear student, in both the cases the nucleophile is NO2 minus. NO2 minus. Whether it is silver cyanide, in potassium nitrate, which one is nucleophile? NO2. Here also which is nucleophile? NO2, because both carrying a negative charge. Here also nucleophile NO2 minus. Here also nucleophile NO2 minus. But here the attack of NO2, this is to carbon through oxygen. It attacks, NO2 attacks through oxygen in the first case. In the second case, NO2, the attack takes place through nitrogen. Attack takes place through nitrogen. Ill note kodi. RONO. Oxygen attacks carbon. Oxygen attacks carbon. Here nitrogen attacks carbon. Therefore, nucleophile is NO2 minus. Nucleophile is NO2 minus. But nucleophilic center is, one is attacks through oxygen atom. Next case, it attacks through nitrogen. Therefore, NO2 minus also very beautiful example for ambidentate nucleophiles. Ambidentate nucleophile. Once again, my dear student, I'll repeat the definition for ambidentate nucleophile. Nucleophiles having two nucleophilic center. Nucleophile having two nucleophilic center are called as ambidentate nucleophile. The very beautiful example for ambidentate nucleophiles are CN minus and NO2 minus. CN minus and NO2 minus. Here in case of potassium nitrate, attacks takes place through oxygen. In case of silver nitrate, attacks takes place through nitrogen. This is known as RONO, is known as alkyl nitrite. Here it is called as nitroalkane. Nitroalkane. Example, C2H5Br plus KNO2. Here nucleophile is NO2. Here Br. Attack takes place through oxygen. Therefore, it will form C2H5ONO. The compound is ethyl nitrite. Here, same alkyl halide heated with alcoholic AgNO2. Nucleophile is NO2. Nucleophile is NO2. Here, therefore, here attack takes place through nitrogen and it will form RNO2. It is known as what? Nitroalkane. Therefore, when you add alcoholic KNO2, you will get alkyl nitrite. When you add alcoholic AgNO2, you are going to get nitroalkane. Nitroalkane. Example, in place of R, you put C2H5. In place of X, you put bromine. Here also, in place of R, you put ethyl, C2H5. Or you can written as it as CH3CH2, CH3CH2 bromine. Therefore, this is about nucleophilic substitution reaction. Therefore, once again, what I had discussed, the nucleophilic substitution I had given in the table. When NaOH is taken, which is nucleophile, OH minus, substitute product is alcohol. Substituted product is alcohol. When you use reagent water, nucleophile is water, substituted product is alcohol. Alcohol. Okay. When you add sodium alkoxide, sodium alkoxide, sodium alkoxide. The nucleophile is R dash O minus. You will get ROR dash. O idre idannu enanta karitivi ether. Ether. Alige when you add reagent sodium alkoxide, product is ether. When you add sodium iodide, you will get Ri, alkyl iodide. When you get ammonia, RNH2. Nucleophile enaguttille NH3, ammonia, it is called primary amine. When you add primary amine, it is known as what? Primary amine. Primary amine. The nucleophile is R dash NH2, you will get RNH R dash secondary amine. When you add secondary amine, it is R dash R double dash NH only nucleophile. There is a formation of what? Tertiary amine. When you add KCN, we will get RCN, that is cyanide. When you add AgCN, you are going to get isocyanide. Okay. When you add KNO2, you will get alkyl nitride. When you add AgNO2, you will get nitroalkane. When you add silver salt of carboxylic acid, you will get ester. When you add lithium aluminium hydride, you are going to get hydrocarbon. So these are the list of reagent, nucleophile and the product name Okay, so this the the table of what? Nucleophilic substitution. Now this already I discussed about ambidentate nucleophile. Okay, so now in this class I discussed completely about the first reaction of haloalkane or alcohalide, that is what? Nucleophilic substitution reaction. Totally 3 reactions comes under alkyl halide. First one is nucleophilic substitution, second one is elimination, third one is reaction with metal. First today I completed the first type of chemical reaction, that is what? Nucleophilic substitution reaction. Okay. In the next session I will explain about the completely depth of nucleophilic substitution reaction. Therefore, today's session I will complete nucleophilic substitution reaction. Next session I will explain the mechanism of nucleophilic substitution. Okay. Goodbye. Thank you all.